to Analog Electronic Circuits, lecture number 3.1. So today we are going to discuss about the low frequency response of BJT amplifier, right? So the circuit in front of your screens is a BJT amplifier. Now, if you look carefully, R1, R2 are my biasing resistors, which will make sure that a DC voltage reaches the base terminal, right? RC is the collector resistance, resistance, right? So these resistance will make sure that your BJT, NP and BJT is biased in the forward active region so that it is eligible to behave as an amplifier. Now let's talk about the capacitors CC1, CC2 and CE. So capacitor CC1 is my input coupling capacitor, which will couple my input AC input to the base terminal of my transistor. Okay, and CC2 is my output coupling capacitor, which will allow your AC to go through and will block the any DC. Will block the any DC coming out of the capacitor CC2. Because if you see, look carefully, your collector terminal will contain both the DC quantity as well as the AC quantity. But at the output, you only want AC. V out is only AC quantity, right? So in order to block the DC component, we connect the output coupling capacitor CC2. Now let's come back to the bypass capacitor. So CE is my bypass capacitor. So any AC signal which is present at the emitter terminal will be bypassed to the ground with the help of CE. Okay, and for a NP and BJT, this is my base terminal, this is my collector terminal, and this is my emitter terminal. Fine, and I have to apply a DC voltage of VCC, correct, to power on the MOSFET to operate in the proper forward active region, and then I have to apply a small sinusoidal AC signal so that it gets amplified at the output, okay, in the AC form only. So in the source side, we have connected a R6 source. So R6 is basically, this AC source VS is a voltage source. So practically it will have some internal resistance. So that internal resistance is represented by R6 over here, right? So VS along with R6 comprise of source, right? At the output, we have a load, resistive load. So RL is called as a resistive load. Okay. So my amplifier consists of this part. This is my source. This is my load. And in between we have the amplifier. So amplifier consists of 4 resistors, 3 capacitors and an NP and BJT. Fine. Source will consist of VS, AC source and RC internal resistance. Load will consist of resistive load RL. Fine. So before I proceed ahead, any doubt in this circuit? If you have any query, you can ask right now. I can explain. Any doubt in this common emitter BJT amplifier circuit diagram? I mean the circuit.
What do you mean by coupling capacitor?
Yeah. So basically what happens is in an amplifier, it should amplify the AC quantity only. But in this configuration, we have the DC quantities also, right? We don't want that the DC quantities are available at the output also. At the output, see carefully. VS is my small AC source. So this is actually pretty small AC, right? And this is being passed via the capacitor. So capacitor will pass all the, see there might be a voltage drop across this also, right? So there might be a voltage drop across this and the capacitor will pass the AC to the base terminal. Now what will happen next will be that this at the base terminal we know we have a IB current. So that IB will be converted into IC beta times, right? So you have an amplified current over here which will be passing to the resistor RC and it will convert itself into a voltage which is amplified voltage. But at the collector terminal we have both AC and DC quantities. So we know that the capacitor has a property to block DC and allow AC. So CC2 will only allow the AC quantities to go through and it will block the DC quantity. If you don't connect this capacitor, what will happen at the output? You will get DC as well as AC, which is not what we want. And the bypass capacitor role is again to allow AC and block DC quantity. So that's the role of these capacitors. Understood? Coupling capacitor meaning it will couple the input to the input of the amplifier. and output coupling capacitor will be, it will couple the collector terminal output to the actual output of the amplifier. Clear? It is clear to you? Yeah. Hello. Yeah. So here, listen carefully. We have to analyze it by step. So step one is the DC analysis. Our ultimate aim is, from the DC analysis, is to find IBQ and ICQ. So for that, we have to draw the DC equivalent circuit. So when you draw, this is just the revision going on. You have all covered this, studied this in your lower semester in BEC, Basic of Electronic Circuits. But I am revising it once more time. So for this, we have frequency. For DC, we have frequency equal to 0. And the reactance offered by the capacitance over here, 2 pi fc. So that will be infinite, right? Because frequency 0 means infinite. So all the capacitors in the circuit will be replaced by open circuit. Okay, CC1, CC2 and CE will be replaced by open circuit, and you will be left out with this circuit over here, which you see in front of your screens. R1, R2, RC, RE and that BJT with the supply voltage VCC. Now you know how to calculate IBQ and ICQ. So you have to convert this into Thevenin's equivalent. So Thevenin's equivalent voltage will be R2 divided by R1 plus R2 into VCC. No need for me to explain this further, because I think this we have covered many times. And RTH is R1 parallel to R2. And IBQ, what is the formula for IBQ? VTH minus VBE. VBE is normally 0.7 if not mentioned. RTH plus 1 plus beta times RE. So beta and VBE are the parameters of BJT. Okay, so I can write it down over here that beta, sorry for that, beta and VBE are the parameters of BJT, which will be given to you in a numerical. Okay, so this beta and VB will be given to you in the numerical. So using that, we can calculate IBQ, and then ICQ will be beta times IBQ. So you have calculated IBQ and ICQ from the DC analysis. That is required. I will explain why it is required. So step one is clear to you, DC analysis. What is the expectation is to find out the value of ICQ and IBQ. Is this step clear to you? Step number one.
Hello,
DC
sir.
analysis. Yeah.
Sir, when we draw the DC equivalent circuit, sir, you said that we replace the capacitors by open circuit.
Yeah.
Sir, so but whenever we connect capacitors to any DC circuit, they have a different that equivalent exponential response, right?
No. We are not, going into that. You see now carefully over here. What is the impedance offered by the capacitance over here? F is equal to 0. F is 0 for DC values, right? So XC will be 1 upon 2 pi FC. F will be 0 means XC will be infinite. And how do you represent infinite impedance? You represent infinite impedance by open circuit.
Sir, but
And you represent. See, listen. This is only to calculate the values of ICQ and IBQ. See, when I say we, represent this DC equivalent circuit, in the capacitors are being connected only. We don't remove them. But for analysis purpose, for calculation purpose, we do that only. Are you getting what I'm saying?
Yes, sir.
For calculating the values of IBQ and ICQ are the DC quantities. So in order to calculate that, we replace the capacitors by open circuit. This is just for our calculation, theoretical calculation. In reality, if you want to do this in a breadboard, you connect everything together, and then you can measure it on the multimeter itself, the DC quantities. But for analysis purpose, we do it like this.
So won't the DC capacitors have any effect on the current then?
Which current?
So the DC current, like I said, that
It will block
whenever
DC current. No, it will not allow the DC current to pass through. Na? That's what the property of the capacitor is. Here it is written clearly. Capacitors will block DC and allow AC to flow through it. Very simple fact. So DC will remain here only. DC will remain here only, and DC will remain at emitter terminal, base terminal, and collector terminal only. It will not forward. It will not
So,
proceed forward.
so can we say that that happens because the capacitor will have a maximum voltage at some instant?
See, we are not applying directly a DC voltage to a capacitor over here. DC voltage is present because of VCC voltage, right? So R1 and R2 will provide VB voltage, correct? And the amount of current which is flowing through the capacitor, through the resistor RC will provide the, the voltage at the collector terminal, right? So yeah, at the collector terminal we have both AC and DC. So what will the capacitor do is whenever it sees a DC quantity, it will block it completely. We are not talking about charging and discharging over here. You are getting into that. I understand.
Yes, sir.
Whenever static voltage has been applied, in charging and discharging also you keep on applying, na, varying the voltages. Varying voltage means AC only, na?
Yes, sir.
So whenever we apply a DC quantity, a capacitor will not allow that. It will only allow the AC quantities. Is this clear now?
Yes, sir.
Yeah. So I am very happy that you all are asking the doubts still, because in spite of studying this topic. Now, why do we calculate ICQ and IBQ? ICQ and IBQ are my Q point currents. Correct? You know what is a Q point, right? In order to properly bias the BJT, I will show it to you. Just a minute. So let's say that you have this characteristics, output characteristics, correct? And you must have studied that you draw the DC load line, right? And where is the Q point? Q point is normally over here. So this is my Q point. Yes or no? This is what you have studied, right? This is VCE and IC, and then this coordinate of the Q point will be going up and down. Here it is. So this will be VCEQ and this will be ICQ. So by DC biasing means we are setting the DC values and the voltages for this transistor to operate in the forward active region. When it operates in the forward active region, only then it will act as an amplifier. Now, let's proceed forward. Why do we calculate ICQ and IBQ? We calculate that to evaluate the small signal model parameters. So what are the small signal model parameters? RPi, GM and RO. Right? We had normally, I think in the last semester you have used hybrid pi model, correct? Hybrid pi model you have studied, right? Yes or no?
Yes, sir.
In hybrid pi model we have RPi, we have GM and we have RO. Right? We will talk about that very soon. We have hybrid pi model also have revised. So these are the formulas. So in the formula of RPi, it has beta VT. VT is the thermal voltage. It's 26 millivolt at room temperature divided by ICQ. Therefore, since we require ICQ here, that's why we do the DC analysis to calculate the ICQ. Okay. And this is the procedure we follow for all the amplifiers, whichever amplifier which we'll be studying about it. Okay. First, we'll calculate the DC analysis, even in MOSFET amplifier. Then we'll calculate the small signal model parameters in the form of RPi. GM is the transconductance. Its formula is ICQ upon VT. These formulas you have to remember. And RO is the output resistance of the BJT, which is VA upon ICQ. VA is the early voltage. I told you BJT concepts you should know. VA is the early voltage. If VA is not given in the numerical, we have to assume that RO will be infinite. Now, infinite meaning it will not be present in the hybrid pi model. Okay. Any query over here in step number 2? After you calculate ICQ, then you have to calculate RPi, GM and RO. Clear about this step? Yes or no?
Yes, sir.
Okay. Next is step number 3. So step number 3 is calculating the midband voltage gain. Don't worry, I will be talking about why this is called as midband voltage gain. But for time being, it's a voltage gain. AV mid, denoted by AV mid. So for calculating it, we draw the AC equivalent circuit, right? So when we draw the AC equivalent circuit, there are two conditions. All the capacitors, it's just a representation for calculation purpose only. All the capacitors are replaced by a short circuit, right? Any independent source. Now, what is the independent source in this circuit? Can anyone tell me? What's the independent source in this circuit, BJT amplifier circuit? Whether it is VS or VCC. Independent DC sources basically. Which is it?
So VCC.
Yes, because it doesn't change with time. So quantities which are not changing with time are not considered for the small signal analysis. Because small signal equivalent circuit will only represent the small time varying quantities, right? So VCC is not a small time varying quantity. That is why we have to replace all the capacitors. I mean, replace the any independent source, replace it by a short circuit. So when we do that, we get this, right? So we have over here, earlier we had over here CC1, we had over here CC2 and CE. All of them are replaced by a short circuit, as you can see, right? And also the VCC is also replaced by a ground. Now, and we have connected everything back. See, VS is my small signal time varying source, and Vout is also AC quantity, so that will remain, correct? Resistors R1, R2, RC and RE will remain, RC and RL also will remain, and here capacitor C is replaced by a short circuit. Now, can anyone tell me why RE resistor becomes redundant? It is visible, no?
So because the current will only flow through the short circuit path.
Yes, the current will prefer the low impedance part. Technical term is that. Short circuit means low impedance part. So basically this short is in parallel to RE, therefore RE becomes redundant. So when RE becomes redundant, directly the emitter terminal is grounded, correct? So this becomes my AC equivalent circuit. Any doubt up till now? I am going slow because these are very fundamental concepts. Any query up till here? Any point not clear? Okay, fine. So now next is step number 4. So step number 4 is replace BJT by its hybrid pi model. So I will tell you now why we do that in reality. See, we want the amplifier to amplify the AC quantity, small AC quantity, and it should produce at the output a magnified, a magnified, correct? But in reality, your BJT amplifier also should be a linear amplifier. Correct? It should be a linear amplifier so that we get a predictable output. If you apply some input, small signal input, we know that how much should be the output. That's called as predictable. But we know that a BJT is a non-linear device. BJT is a linear or a non-linear device? BJT is a linear or a non-linear device? Anyone? What is this characteristics looking like? Can anyone recognize what is this characteristic in a BJT? Which characteristics is this?
Impedance increase.
Sir,
What?
sir, input.
Correct. And output characteristics you already know. Output characteristics will be how it will be. Correct, na?
Yes, sir.
Huh. So now, can you say, looking at the characteristics, that the BJT is a linear device? This will be IC. What will be this? VCE. So this is my output characteristics. This is my input characteristics. So looking at the characteristics, can you say that BJT is a non-linear device or a linear device? Linear or non-linear?
Sir, it can be linear in a certain range, right?
Yes, it can be linear, but right now in a overall range it's non-linear, right?
Yes, sir.
So BJT is non-linear. But what are we doing by drawing the hybrid pi model? We are linearizing the non-linear BJT. We are linearizing the non-linear BJT, right? So that's the definition. That's why we replace it by a hybrid pi model. So when we replace the BJT by its hybrid pi model, now we are treating it as a linear device. Correct. Here we have, this is my hybrid pi model. So now will BJT is a linearized version of the of itself. Okay. So now this is my, if I want to replace a base collector and emitter. So of terminals of a BJT. So I will do like this. So between my base and emitter, I have R pi resistance, and the voltage across this is V pi, correct? And then we have between IC, between the collector and the emitter, we have the voltage dependent current source, GM into V pi. And then we have also RO, which is the output resistance of the BJT. Okay, so there are three quantities: R pi, resistance, GM V pi, current source, and RO, again resistance. Okay, so this is my hybrid pi model. You all have been taught in this fashion only, no? Anything different which I'm talking about, just let me know. Everyone comfortable with the hybrid pi model? Any doubt over here? Hello? Everyone clear about it?
Yes, sir.
Okay, okay. I will share separately a recorded video where I've explained how this hybrid pi model is a linearized version of the BJT. So you all can refer that for further details. I'll share it after the lecture. Next is we have to insert the hybrid pi model in the AC equivalent circuit. So this is my AC equivalent circuit here. We have to replace the BJT by its hybrid pi model, and we have done exactly over here like this. Okay. So first of all, we have drawn the hybrid pi model, and we have assumed RO to be infinite for convenience or for better simplification. So we have assumed RO equal to infinite. If not, we have to consider RO everywhere, right? So here right now in the analysis, RO is infinite. So we'll draw the hybrid pi model first. So R pi and the voltage across this will be V pi. Then we have GM V pi current source, right? Then at the base terminal, what do we have? We have resistor R1 and R2 in parallel. So that is what we have drawn over here, R1 and R2 in parallel. Then in series, we have a resistance and a AC source. So in series, we have a resistance R6 and AC source. What is there in the emitter terminal? Emitter terminal is directly grounded. So emitter terminal over here is directly grounded. Then at the collector terminal, what do we have? At the collector terminal, we have two resistance RC and RL connected to the ground, right? So here it is. RC and RL, they are in parallel, but they are connected to the ground. And then we have V out. So this is called as mid-frequency, mid-band, small signal equivalent circuit. This is called as mid-frequency, mid-band, small signal equivalent circuit. So why do we draw this equivalent circuit? To calculate voltage gain, AV mid, right? So can you tell me what will AV mid will be output voltage divided by the input voltage. So it will be V out upon Vs. Okay. But what is the input of the amplifier? Input of the amplifier, I can call it as a V in. Why I am calling it as a V in? Because Vs and Rsig are together. Because Rsig is the internal resistance, right? So that becomes the source. Now V in is the input of the amplifier, Vs is the source, voltage source, and V out. So we can write AV mid as V out upon V in into V in upon Vs. It means V out upon Vs only. Are you understanding this point? Is this clear to you? Hello?
Yes, sir.
Okay, fine. I will explain why it is called as mid frequency or mid band slightly later on when we will discuss the numerical of it. So why it is called as mid frequency or mid band small signal equivalent circuit, I'll clarify it. Now I am not going into details of the derivation. If we derived it, V out upon V in will come out to be minus GM into RC parallel to RL. Okay, so I'm assuming that you all already have gone through the derivation of voltage gain for a common emitter amplifier, and we can write it like this. Then we have V in upon Vs. Okay, now V in upon Vs is again can be calculated by a voltage divider rule over here, right? So again, I'm not going into details of it. You all can find it out on your own based on your circuits covered in your BEC. So V in upon Vs formula will be R1 parallel to R2 parallel to R pi divided by R1 parallel to R2 parallel to R pi plus R6. So once you know the V out upon V in and once you know V in upon Vs, you multiply them and you get AV mid, right? And once you get AV mid, you calculate it in dB. So AV mid in dB will be 20 log to the base 10 of AV mid value. Okay. So the ultimate aim of drawing the small signal or the mid-band or mid-frequency small signal equivalent circuit is to calculate the voltage gain, right? It's always a good practice to draw the mid-band small signal equivalent circuit. So you don't have to do this much in the numerical. I am written this for your reference. In the numerical, when we write step 3, directly you should be capable enough to draw this mid-frequency small signal equivalent circuit directly. No need for any explanation or something. You should know the formula, right? Or you can derive it very quickly and find out the voltage gain. Any doubt in this step? Any doubt before I proceed ahead? In the mid-band small signal equivalent circuit or the formulas, how it has come, because the actual topic will start now. Clear it is? Okay.
Yes, sir.
Okay, fine. So now we will begin. So yeah, this is what is new in this semester. You have to calculate the low cutoff frequency of the circuit, right? Which circuit we are talking about? We are talking about the BJT amplifier circuit. Okay, for this BJT amplifier CE and BJT amplifier, we have to find the lower cutoff frequency. I will tell you why we calculate only lower cutoff frequency, right? So for this, there are two steps. We have to draw the low frequency small signal equivalent circuit, and then we have to calculate the low cutoff frequency due to three capacitors which we have: FL of CC1, FL of CC2, and FL of CE, right? There are three capacitors, external capacitors connected. So each of them will provide a lower cutoff frequency, right? I will talk about it details right now. So to draw the low frequency small signal equivalent circuit, what do? We keep the capacitors as it is in the AC equivalent circuit. We'll keep the capacitors in the AC equivalent circuit and will replace only the independent sources by a short circuit. Okay, so that is what we will do. So we have seen now the mid-band small signal equivalent circuit. Here, if you consider the capacitors as it is, how the circuit will look like? It will look something like this. This is the same circuit only which we have drawn earlier. Only thing is we have added the capacitors as it is. So remember, the resistor RE was getting redundant. Now it will not get redundant because CE is not connected to the ground. It's not short circuited. So therefore we have capacitor CE, CC1 and CC2 as it is. Okay. So I'll request all of you all to draw. You all will not be able to draw this, but when I write something over here, you all also write along with me. Okay, fine about it. So one way to check whether this is correct. So what you do is you can in your mind just replace all the capacitors by a short circuit in your mind. Don't do it on paper. But if you do that, you will get back your mid-frequency small signal equivalent circuit. If you replace the capacitors by a short circuit in your mind, then you will feel that you will get the same circuit over here. Okay, so that's the way to check whether our analysis or your circuit low frequency equivalent circuit is proper or no. So if anyone asks you to draw the low frequency small signal equivalent circuit, we have to keep the capacitors intact. Rest all the procedure remains the same. Is this point clear? Because this is something new which we are talking about. We are drawing the capacitors in the equivalent circuit only, small signal equivalent circuit itself. Any doubt over here? Yes, no, what?
No, sir.
Okay, now start writing along with me. Yeah, so first of all, we'll start by calculating FL of CC1. So what is this FL of CC1? We'll see that shortly now. It is nothing but lower cutoff frequency due to CC1 alone. Okay, It is the lower cutoff frequency due to CC1 alone. And I have to draw the small signal low frequency equivalent circuit again. Yes, you have to do that. So for this, we have to adopt a certain rule. So what are the rules over here? The rule is we have to short circuit. Since we are considering the lower cutoff frequency due to input coupling capacitor CC1 alone, we have to short circuit CC2, capacitor CE, and voltage source, input voltage source Vs. We have to short circuit. This is the rule which we have to follow. So we have to short circuit CC2, capacitor CE, and Vs, voltage source. Are you all with me? You all are writing it down along?
Yes, sir.
Okay. Now let's practice by drawing the low frequency equivalent circuit. Okay. So first of all, we'll draw the small signal. So small signal model is, let me take a black color. Yeah. So small signal model will consist of R pi. This is my R pi resistance. Here I have my base terminal, and here I will have a voltage source. So you can also draw it in your books. I mean the current source, sorry. This is Gm into V pi. Where is my V pi? Here is my V pi. Okay. So this I have drawn the hybrid pi model, and I'll write the terminals now. Base, collector, and emitter. Now tell me what will remain and what will go. So CE will be replaced by a short circuit. So does the emitter terminal will be connected to the ground, or a resistor RE will be there? CE is replaced by a short circuit. What will happen? Emitter terminal connected to the ground, right? Yes, now because this will be replaced by a short circuit, so RE will become redundant. Agree or no? Hello?
Yes, sir.
Okay, fine. So what you do is you just connect it to ground. Now, what will happen at the collector terminal? At the collector terminal, we have a resistor RC. So there is a capacitor over here will replace by a short circuit, and then we have a RL over here, and we'll ground the other part. So this is RL, and over here we have the output. So V out is over here, right? Remember, output is a AC quantity. And at the base side, what do we have? We have a resistor R sig. Then we have a capacitor. Correct? We have this capacitor, and then it is connected to R1, R1, R2 in parallel. They are connected in parallel. So this is my R1 parallel to R2, and then I have a voltage source. This is my AC voltage source Vs. So this is again a AC quantity. Remember that. This is a small signal model, right? I mean small signal equivalent circuit. So this is the low frequency small signal equivalent circuit for calculating the lower cutoff frequency due to CC1 alone. Okay. So this is my CC1 voltage, CC1 capacitor, CC1. Okay. Have you completed the drawing? Have you understood how do we draw it? Clear it is?
Yes, sir.
Okay. Now I will tell you something. You have to listen very carefully. So I will draw the same thing in the form of a system, right? So let's say that we have this resistor R sig, and then we have a capacitor, and then we have a voltage source like this, and then we have a system over here. Okay, and this is terminal also, right? This is connected to the ground. So this is my voltage source, small signal voltage source Vs, where R sig is a part of that voltage source, right? Because they are together. This is my CC1. Okay, so what we have to do is we have to find out what is the equivalent resistance over here looking into the system. So that equivalent resistance, we call it as Ri. What is the resistance looking into the system, right? This is a system, right? So what is the resistance, input resistance looking into the system in terms of Ri? Is this point clear to you? We have to calculate Ri now. So why do we do this? I'll explain it to you at the end. But right now we have to do this. Right? We have a system. It can be an amplifier. It is an amplifier in our case. And we are having CC1. And then we are applied to that system. So we have to calculate Ri. So why do we do this? Remember in the last lecture, we have studied something like this. Let me take slightly up. I guess we have completed a circuit which looks like this, right? We have a R into C. This kind of a circuit we have studied. I have told you all to refer the recorded video wherein I have explained this. And that's my V out. Correct. Does anyone remembers what will be the frequency response looking like for this circuit? How was the frequency response? Was it like this?
No, sir. It was the other way around. It was going downward.
Like this, no?
No, sir.
It is like this only. When it was R and C over here, then it was the way you were telling.
Acha, ha. I recollect it.
Simple way to remember is, for low frequencies, this capacitor will behave as open circuit. When it behaves as open circuit, the input will not reach the output. So at low frequencies, your circuit will attenuate. And then at a cutoff frequency, when you go 3 dB down, this is actually the, I think, V out upon V in, no? Correct? So this we used to call it a voltage gain. And this is the frequency. Right? So this frequency, what was it called it as? Cutoff frequency. And F0 was given by, what is the formula? Anyone remembers? F0 is the cutoff frequency. What is the formula for it? Quickly. What is the formula for F0? We have done this in the last class.
So 1 upon 2 pi RC.
1 upon 2 pi R1C1. Okay. So that's why we are doing in this manner. I mean, this is the reference which we are using, right? And that's why we are applying to this system also. Now, same thing can be applicable, because what happens is, you will say, sir, RSig is there, na? So RSig is a part of AC source only, na? Yes. So that's why C and Ri, we have to consider it in that sense. Now, if you tell me what will be your Ri over here, if you can identify, what will be Ri over here? So what is the system I am talking about? Which is the system? The system is this, right?
Yes, sir.
This is the system. And here we have to find the value of Ri. Now, help me to find the value of Ri. Can anyone tell me what is the value of Ri? What do you, if you stand over here, which resistance do you see?
Sir, R1 in parallel with R2 in parallel with R pi.
Yeah. Why R pi is in parallel with R1 and R2? Because see, here also it's connected to the ground in parallel to R pi. Why don't we consider RC and RL? Why don't we consider RC and RL? Anyone? Because the reason being, I will tell you right now, the reason is very simple. The impedance of looking into the current source is infinite. So anything parallel to infinite has no meaning only itself, right? That is why Ri will be equal to R1 parallel to R2 parallel to R pi. Is this point clear? This is very, very crucial. How to identify Ri. Is this point clear to you? Everyone? Yes or no? I can repeat that point, no problem. But you have to understand.
Not clear, sir.
Which part not clear?
that why don't we take RC and RL?
See, if you look into over here, this is open circuit, na? Open circuit has infinite resistance. Simple as that.
Okay.
See, between the base and the collector, there is no wire connected, na? If it was a wire connected, still the resistance would have been infinite. The
So
resistance
we could
offered
consider
by
RC and RL, right?
no, we cannot consider RC and RL, not at all, no question, because right now base and collector terminal are open circuited. You remember in a BJT, base and collector are reverse biased, so no current flows. So if no current flows through base and collector, then we say it's a infinite resistance. Yes or no? So that's
Yes,
the.
sir.
Did you understand now why we cannot write
Yes, sir.
further RI value? Yeah. Okay, fine, good enough. So now if I redraw the same circuit below, if I redraw it the same circuit below like this, so I have my voltage source. You all also keep on writing, please. This is my Vs, and I have a RS, RSig over here. Then I have a capacitor CC1, and I'll go a little down, and then I have Ri in the circuit. Now it has become very simple as for us to write. And also one more condition was there, na? What was the condition? Short circuit Vs also, correct? So what will happen if we short circuit Vs? Short circuit Vs means what? This terminal will be connected to this terminal. That will make Vs is equal to 0. Okay. So now, what is the situation over here? What do we have on the, let's say this is the left plate of the capacitor. So in the left plate of the capacitor, I have resistance Rsig, and on the right plate of the capacitor, I have resistance Ri. So now if I have to apply this concept over here, that F naught is 1 upon 2 pi R1 C1. So what will be the, again, the, I am asking what will be the formula for FL of CC1? What will be the formula? It will be given by 1 divided by 2 pi. We call it as R equivalent. R equivalent into CC1. Okay, just a name, just a terminology. So over here, similarly, we have R1, na? We have only R1, right? Here, what do we have? Do we have Ri only, or we have Rsig also? We have Rsig also, na? So that also has to be considered. So how are they connected? Are they connected in parallel or are they connected in series?
So in series,
Yes. So what will be R equivalent?
R1 plus R sig.
Yes. How to remember? On one side or left plate of the capacitor we have Rsig, on the right plate we have Ri. So R equivalent will be Rsig plus Ri. So therefore, finally, if I want to write the formula for FL of CC1, it will be 1 upon 2 pi into Rsig plus Ri into CC1. So that's the formula, which you should remember. Sorry for that. Yeah, this is the very important formula which you should know. So please note it down, everyone. It is clear to you how we have got it. Basically, this R equivalent into CC1 is nothing but my time constant only. This is nothing but your RC time constant only. So this is FL of CC1 only due to CC1. So this is my lower cutoff frequency only due to coupling capacitor CC1. What will happen if Rsig is 0? It will disappear from the formula. It will be 1 upon 2 pi Ri CC1. And here we can write where Ri will be given by R1 parallel to R2 parallel to R pi. Is this clear now? Hello? Everyone, is this clear? Is this point clear to you?
Yes, sir.
Okay. Now, similarly, we have to find out. Let me just go up. This is the first step, right? For calculation of FL of CC1. I'll just write these things and you can try it out and we'll continue tomorrow. But let me write this few lines over here. I'll go to this tool and you all have to write it again, but I can easily copy this part. Okay. So now I will go down and I can I'll paste this thing over here. Okay. So over here, I will write over here carefully. This is the second point. Okay. For FL of CC2, you all have to write it again. Let me use an eraser over here. Okay. FL of CC2 it will be. Lower cutoff frequency due to FL of CC2. Here I will be having CC1. So please add this thing. This is step number, we are doing the second scenario. Calculate FL of CC2, which is the lower cutoff frequency due to coupling capacitor CC2 alone. Okay. So we short circuit CC1. Sorry for this. We short circuit CC1, CE and VS. We short circuit CC1, CE and VS. And then we find the lower cutoff frequency due to CC2 alone. We'll find the lower cutoff frequency due to CC2 alone. And I guess that we will continue in tomorrow's class, in the next lecture. Okay. So we have to calculate FL of CC2. Then FL of CC1 we have already evaluated. We have to just calculate the formula or the expression for FL of CC2. And then finally FL of CE. And yeah, that will be representing a low frequency response. Fine with this? Any doubt over here? So far we have covered today. If you have any doubt, you can ask. I can just, glance through the topics one more time. Let me revise what we have covered so far. So we have started with BJT amplifier, right? What is the role of every component over there? The importance of the coupling capacitors and the bypass capacitor. Then the significance of the DC analysis part. Then in step 2, we calculated the small signal model parameters, R pi, GM and RO. Then we calculated the midband voltage gain AV mid. I have given you all the technique. We have seen the hybrid pi model also. And these are the formulas for the calculating the midband gain. So next time also we'll be solving a numerical. So all these things will be necessary. Then we came to a new topic, that is calculating the lower cutoff frequency of the circuit, that is FL. So in that we have drawn the low frequency small signal equivalent circuit, and we have to calculate FL of CC1, FL of CC2 and FL of CE. So we have drawn the low frequency small signal equivalent circuit, and this was the circuit with the capacitors inside. Then we wish to calculate FL of CC1 alone, right? It is a lower cutoff frequency due to CC1, and there were some rules in drawing this circuit. And finally, we found out the expression for FL of CC1, which was 1/2 pi into R6 plus Ri into CC1, right? Where Ri was R1 parallel to R2 parallel to R pi. And then we are going to cover next time the procedure to calculate the expression for FL of CC2, which is the lower cutoff frequency due to CC2 alone, right? So far, whatever we have covered, any doubt you all have? Yeah. Everything is clear. We have gone very slow. So if you want me to repeat anything next time, I can do that, but please let me know right now. Okay. So our plan for next, yeah. Okay. So our plan for next time will be, we will derive the expression for FL of CC2 and find out the expression of FL of CE, and then we'll solve a numerical based on this. Okay. So that is a plan for next lecture. So be ready with your calculators, right? And keep everything ready in your notebooks, right? So that is all for today. Thank you everyone for joining. Please revise the topics. We are going very, very slow. Once this one frequency response is covered, low frequency response analysis of BJT amplifier is covered. For MOSFET amplifier, it will be very, very simple. Okay, so please give all your attention and all your practice to this initial numericals or concepts which we are discussing. Okay, so that's all for today's session. That is analog electronic circuit session number 3. So we'll meet next week, I guess. Yeah. So thank you everyone for joining.